Hello, this is Mickey Urdea for Altaris Associates, and welcome once again to one of our episodes of Interesting Stories in the History of Diagnostics. Last episode, I talked about cancer diagnostics, and I started out with sort of the history of cancer itself, all the way back to the dinosaurs. I talked a bit about the Egyptian mummies and the evidence of cancer in them, and I ended with discussion about some of the early markers that have been used in cancer diagnostics. A bit about X-rays, a bit about early protein markers from, for instance, Centocor, and then alpha-fetoprotein and CEA. Today, I'm going to pick up where that left off, and I'm going to talk about the astonishing array of technologies and test types that are now available for cancer. It's just amazing how quickly this field is moving. And in fact, it's moving so fast that I won't be surprised if in 2 weeks, a lot of what I'm going to say is passé already, but just bear with me. I want to start out by talking about the types of tests that are used in cancer. There's quite a variety. You're probably very aware of, for instance, screening. There are a number of different types of screening tests. There's mammography, many others, PSA for prostate cancer. We have then the actual diagnosis of cancer. There are a variety of methods to use for that. I'm going to go into a number of those today. Once you have a diagnosis, often there is then a staging process, a number of ways in which that is done, but gives the physician a sense of how far along the particular cancer is. Then once that information is available, there are occasionally prognostic tests, and I'll talk a bit about that today, which can help to determine the aggressiveness of the intervention that should be taken. Then there is the actual selection of therapy. And in many cases, we have tests today which are able to help the physician and the patient to determine which particular drugs are more likely to work than others. And then there is a monitoring phase, if such tests are available, to determine how well it's actually working or not. So you can make a decision about whether or not to change the intervention. And then finally, after the cessation of therapy of whatever type, there are often then now, and more as time goes on, so-called recurrence tests. Actually, there are now tests which are being used for both the monitoring of therapy as well as the recurrence, and those are referred to often as minimal residual disease tests, and I'll talk a bit about that today as well. I'm going to organize this into what I guess I can call biological structure organization. And specifically, I want to talk first about the process of using the entire body to look for presence of cancer, and then take a step down and talk about tissues and cells. And then the third level is going to be particular molecules that are used. And that's going to be the basis of a third episode that we'll come to later. Besides those three levels, there's one that I'm just going to have to call in between. And it's in between cells and individual molecules. And we'll talk a bit about extracellular vesicles in that regard and how those are being used today. So this is going to be a survey. So I'm not going to go very deep in any one thing. I just don't have time for it if I'm going to do the survey. But what we will do is come back later and talk about specific technologies and capabilities and applications in cancer to take a deeper dive very specifically in things that are particularly interesting. So the first category is whole body analysis, if you will. And of course, the most typical and oldest form of this would be actual clinical examination, taking a look at whether there's actually evidence of a tumor, which could be something bulging through the skin. It could be simply visible within the urogenital tract, or it might be skin cancer. So that's the oldest form of this type of detection. But nowadays, the physician's eyes are extended, if you will, by a number of technologies. For instance, I talked last time about X-rays, really the first form of cancer screening for breast cancer, all the way back to the 50s. But we have so many other methods now. We have CT scans, we have PET CT scans, we have MRI. We have a number of ways in which the tumor is identified, localization is determined, if it's large enough, and then the volume is determined. And often that can be done over time with potential interventions, such as neoadjuvant therapy, surgery, or even to determine whether or not the tumor is in an inoperable position, which is unfortunately the case in some cases. Often these imaging technologies involve some sort of contrasting agent, which could be a dye, it could be radionuclides, it could be a number of ways in which to attempt to enhance the visualization of the tumor within the body. So I'd like to talk about some of the exciting advances occurring in imaging technologies that are happening right now, and it's just amazing how much progress there is. For instance, in the case of CT scans and PET CT scans, the number of slices that can be looked at is increasing dramatically, and the time to do that is decreasing. The radiation dose is decreasing, and there's just so much better resolution of the tumor that is possible now. I was talking to a friend recently about this who does a lot of work in this area. He was telling me that the length of time it takes for a PET CT scan that used to be 30 minutes in length now can be done in as little as a minute, which is just amazing. Another area is what's referred to as hyperspectral imaging. Now, this is a form of imaging where instead of looking at the entire picture and taking one spectrum of it, and now this could be a variety of different wavelengths of visible and near visible light. Instead of taking just one picture, it's a matter of taking many, many pictures, basically pixels of individual spectra that is used for the analysis. So it's incredibly data intensive, but it's been remarkably useful in a number of areas, including things like archaeology and agriculture. But there have been a lot of applications in medicine over the last many years, and many of those, in fact, the bulk of them are in oncology. Most recently, it's been very interesting to see that a group at MIT, this is Angela Belcher's group, has been using hyperspectral imaging to look at the presence of tumors right through the skin. And as a matter of fact, they recently reported that they were able to detect a 1 millimeter tumor 7 to 9 centimeters below the surface of the skin using near IR spectra directly on the individual. So, there's no contrasting agents. There's nothing like that. It's looking directly at the tumor. So that's quite interesting and unusual. Another area that I thought was quite interesting is the use of what is called hyperpolarization in MRI scans. Now, this is a fascinating area where there actually is about 100,000-fold improvement in the detectability of cancer cells by using this hyperpolarization method. And that is then used with standard MRI equipment. Now, what's really interesting about it is that they're able to visualize metabolic changes within the cancer cells. Cancer cells are really geared towards growth, not simply static metabolism. So that involves a number of changes. For instance, in the conversion to anaerobic glycolysis and actual reversal of the Krebs cycle in order to start generating materials required to actually build new cells. And those changes are being visualized directly using this hyperpolarization method to increase detectability. Companies such as GE are involved with that. This is based on an observation was made in the 1930s by an individual named Warburg, and it's called the Warburg Effect, which fell out of fashion for a very long time, but people are coming back to it now and recognizing that these metabolic changes are very important to take a look at. There's a really great chapter in a recent book by Nick Lane, one of my favorite scientific authors, in his book called Transformer that came out last year on this effect and sort of the details of metabolism changes in cancer cells. So let's move on to the next level then, and this would be tissues and cells. And I'm going to start with blood-based cancers, so-called hematological cancers. And of course, now you've got an opportunity to take a look at the cells by sampling blood. And a lot of the technologies that are being used for that are looking at the number of cells, the morphology of the cells, and even differences in contents in and on a cell. The most popular technology for this, of course, is flow cytometry. And it's just amazing how sophisticated this has all become and how useful it is. And there's a whole area which is referred to as immunophenotyping, which is commonly used for leukemias and for lymphomas. And the newest technologies out there, and there are a number of companies working in this area, are very sophisticated in terms of number of labels. So as an example, Thermo Fisher's most recent advent in this field uses 14 different colors in their kits with 6 different fluorescent detector types. It's amazing what that number of different types of colors that can be analyzed and the number of types of labels that can be derived from combinations of them are now possible. It's just amazing. So the level of detail that we're able to see now with flow cytometry and labeling is at a completely new level. So in contrast, when we're looking at solid tumors, it's a different set of technical approaches, but similar in many ways. So the most common way to take a look at solid tumors is to actually take a biopsy and then to visualize that biopsy, typically with standard microscopy. And this would be using dyes of a variety of types. This goes all the way back to Paul Ehrlich in the 1880s and the work he did in staining cells. He just was crazed over dyes and used many different types to look at a number of different disease states, including cancer. He actually came up with the first way to classify lymphomas based on their appearance within stained samples in microscopy. If you take a look at a pathologist laboratory nowadays, it's going to look an awful lot like Paul Ehrlich's did way back in the 1880s. There are very well-trained individuals peering into their microscope and analyzing what they see. And they're analyzing the cancer for potential diagnosis and also for staging. And staging then leads to potential scoring that has been developed over the years. For instance, the famous Gleason score, which is used in prostate cancer. Now, the exciting changes that are occurring there tend to be not just the optics for the microscopist, but also the use of AI and machine learning in helping to analyze the pictures themselves. The reason for this is to both increase the throughput, decrease the cost, and hopefully improve the accuracy. Today, there's a lot of work going on in this area. Most of this microscopy work is still done by individual pathologists, but more and more automated systems are coming along. In most cases now, there are still what they're referred to as flag rates. That is the number of samples that the automated system just can't resolve. So those are actually assembled in software so that the pathologist can come take a look at those pictures and resolve the issues. So the pathologist isn't out of the picture yet, and they may not be for a long time, but certainly with the advances in AI and machine learning, we would expect that the process and the quality of the result is going to increase over time. All right, so in this episode, we got through the whole body level. We got through tissue and cells, although I'm going to come back to that a little bit, as I mentioned before. But that's it for this episode. And next time, I'm going to begin with the analysis of individual molecules. And that's a very broad subject that, as you will see in the next episode. So thank you very much for watching this episode of Interesting Stories in the History of Diagnostics. This is Mickey Urdea for Hyperspectral Associates. Thanks very much. Bye.